Hi, my name is Sydney Tuttle, and this is my lab for oscillations. In this lab, we examined the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. In other words, we examined the motion of a mass oscillating vertically on a spring, and we compared the computational and observed model using Newton's second law and the energy principle. We plotted the energy changes in kinetic, gravitational, and spring energy. Overall, we found that the Y data better represented the computational model and that the model upheld the energy principle. In order to do these computations, we had to use Newton's second law, the energy principle, and spring stiffness. We showed that the final velocity equals the initial velocity plus the net forces over mass times delta t, and that the net forces equals mass times acceleration, and the net forces also equal the force of the spring plus the force of gravity. In addition, we use spring stiffness in Hooke's law, which is the force of the spring equals negative k sub s times the magnitude of L minus L naught times L hat, and the force of gravity equals mass times the gravitational constant. In addition, we also use the energy principle, which shows that delta E equals W, and W is equivalent to delta K plus delta U sub S plus delta U sub G, which is the potential spring energy and the potential gravitational energy. Delta K is also equal to 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. In addition, delta S is equal to 1/2 the spring constant times S sub F squared minus 1/2 the spring constant times S sub I squared. And the change in potential gravitational energy is mg times y sub F minus mg y sub I. To begin, we analyzed a video of a mass in a spring and tracker using a set distance of 0.7 meters as the calibration stick. We found that the time for one oscillation was 1.23 seconds, using the time it took for 3 oscillations to occur and dividing that by 3. This is the time it takes for it to swing back and forth in one periodic motion. From there, I recreated the motion in GlowScript. I knew the mass to be 0.402 grams, the initial position to be negative 0.126, negative 0.650 meters, and the initial velocity to be 0. Also, I used the gravitational constant of 9.8 meters per second, and the spring constant we found to be 6.8, and the relaxed length of the spring was 0.123 meters. From there, I defined my L to be the ball's position minus the spring's position, L hat to be the normal of that L, and S to be the magnitude of L minus L naught. The kinetic energy was 1/2 times mass times the magnitude of velocity squared. The gravitational potential energy was mass times gravity times y, and the potential spring energy was 1/2 k sub s times s squared. Overall, the total energy would be k plus the gravitational potential energy and the potential spring energy. From here, I found the force of gravity to be equal to the unit vector in the negative y directions times the ball's mass times the gravitational constant. In addition, the force of the spring would be equal to L hat times S, which is equal to the magnitude of L minus L naught times the negative spring constant. The total net forces would be equal to the force of gravity plus the force of the spring. From here, I updated the object's velocity using that the final velocity would be equal to the initial velocity plus the net force over the mass times delta t, which is Newton's second law, and I updated the position saying that the object's final position would be equal to the initial position plus the velocity times delta t. I also updated the spring, saying that L would be equal to the ball position minus the spring position. L hat is the normal of that L, and S is the magnitude of L minus L naught. In addition, I also calculated and recorded the energy changes as the motion continued, which was the same formulas as before, just using the current minus the initial for both kinetic, gravitational potential, spring force, and the total energy. As a result, I received 2 graphs, one showing the position versus time, and the other showing a change in energy versus time. In the position versus time graph, the computational model is shown in blue, and the experimental model is shown in red. The red graph is tracking the y values of the experiment. It follows the computational model much more closely. The x values were way farther off. I believe the difference between my graph and the computational graph are due solely to human errors in tracking. Overall, the energy principle is satisfied. Total energy is shown in orange and is equal to 0. Kinetic energy is shown in blue. Potential spring force energy is shown in red, and potential gravitational energy is shown in green. You can clearly see the oscillations and the relationship between the spring force energy and the gravitational energy. When comparing the oscillations of the x and the y has an oscillation of 1.45 seconds and x has an oscillation of 1.73 seconds. This is due to the fact that there are spring and pendulum forces acting in the x direction.